Okay, so let's start today's lecture. Okay, so now for today's lecture, okay, so we are going to continue with what we have been left on last lecture. Okay, so last lecture, by the end of last lecture, we've been talking about homogeneous equations with constant coefficients. Okay, so and by this it means that so we've been talking about linear second-order ordinary differential equations. Okay, so a typical linear second-order ODE is going to take the form that it has some coefficients there. It's going to be a linear structure in the equation. Now, for any such equations, okay, so for any such equations, we would like to turn this equation into an equation in standard form. Okay, so we'd like to turn this equation into an equation in standard form. By standard form, it means that the leading coefficient, okay, so the leading coefficient in front of the highest derivative is going to be 1. Okay, so now once you have that kind of equation, you make the equation homogeneous by setting the right-hand side into 0. Okay, so that's a homogeneous equation. In particular, we've been talking about an equation that has a constant coefficient, linear second-order homogeneous equation. So that's a constant coefficient means that the coefficients A, B, C are constants, and homogeneous means that your right-hand side is 0. So that's a linear. Okay, so this is a linear. Okay, so constant coefficient. Okay, so and second order homogeneous equation. Okay, so that's a linear constant coefficient second order homogeneous equation. Okay, now the point here is to ask such questions. Can we solve it, right? So how do we solve such an equation, right? So how do we solve such an equation? Is it good? You can hear me? Yes.
Yeah,
So
yeah, I hear you.
if you have problems with your sound, you might need to like adjust adjust the lower right left corner. There is a microphone like button, and you have to kind of work with it. Maybe it's your phone, your speaker has been turned off. Yeah, just double check. Okay, so okay, let's continue. So that's we are going to talk about how to solve, right? So how to solve this type of equations, right? So how to solve such equations, right? So that's the question. How do we solve such an equation? Is it just by previous method, right? So and or you have to invent something new, right? So that's the point. Now, how do we solve such equations? Okay, how do we solve such equations? Well, the way you want to solve these kind of equations, okay, so the way you want to solve these kind of equations, we must look at, okay, so we must look at what other methods we've been talking about so far, right? So we've been, what other methods we've been talking about so far, right? So and now so far, how many ways to solve differential equations that we have been really talking about, right? We have been really talking about. Well, we've been talking about the method of separation of variables, and we've been talking about integrating factors, right? So these are methods that help you to solve first order equations, but can they help you to solve second order equations? Well, if you if you have been thinking about this problem once in a while, you're going to realize that it doesn't really work. Okay, so it doesn't really solve this equation. So that comes the problem, right? So how are we going to solve an equation of this form? Ay double prime plus by prime plus cy is equal to 0, where a is not equal to 0. The reason why we said a is not equal to 0 is because we want to have an equation that is essentially a second order equation. If a is equal to 0, then you become a first order equation. It's not a second order equation anymore, right? So that's kind of the thing, right? So that's why we want to have second order equations. So that's the point, right? So So therefore, we would like to start discussing this. Okay, so how are we going to solve it? Well, there is no other method than guessing, right? So that's, so far, there has been a very important method of solving differential equation that we really didn't talk about, is guessing a differential equation, right? So that's guessing. It means that you want to guess a solution. There's no method, but rather than guess a solution, because you really don't know how to deal with the second order derivative. So that's the point. But how do we guess a solution? Well, you look at the equation, right? So you look at this equation. It looks like it says that the derivative and no matter how many derivatives you take, you do a linear combination of these functions with derivatives, it results in a 0. So what function, for what function, then after, no matter how you take derivatives, you see it actually, this one can be written as ay double prime plus by prime is minus c of y. So that means that you have a function that you take derivatives of that function, you should come back to the original function, right? So if you come to continue to take derivatives of a function, then you should come back to that function, right? So for what kind of function, is going to satisfy such a property that if you take a derivative of this function, it comes back to itself? Can anybody answer me this question? If I want a function that you take a derivative of this function, it comes back to the function itself. For what kind of function it's going to satisfy this property? Anybody has some good idea? Anyone? Okay, so trigonometric, cosine, sine. Well, that's a good idea. Okay, trigonometric, cosine, sine. But cosine and sine, you take derivatives, they're going to alter between the two, right? So like you take a derivative of sine, that's cosine. That's derivative of cosine, that's sine. It really is not kind of coming back to itself. I want a function. Okay, so this is going to test your calculus knowledge. I want to have a function that if you take a derivative of this function, it is going to come back to itself. What's that function? What's that function? This is a very basic calculus question. It's e power, right? So that's, you're right. Okay, so thank you very much for your answer, right? So it's an exponential function. So that's why we want to say that you guess a solution. When you guess a solution, we want to say that the solution that we would like to guess must take the form that y of, let's say a function of t is e power of t. You want to try this. Now, if you want to try this, you're going to see that if just the e power of t is not going to work, because e power t derivative e power t, it means ABC, you take a sum of ABC, it must reach 0, which is not exactly what you want to have, right? Which is not exactly what you want to have. So that's kind of problem with this e power t. So we're going to try a function. Okay, so we're going to try a function that takes the form e power of rt, right? So where r is to be determined. Right, so r is the parameter that you would like to determine it. Okay, so r is to be determined. Now, how do we determine r? Well, you can just take derivatives. Y prime of t is equal to r times e power of rt, and y double prime of t is equal to r square e power of rt. This is just by basic calculus rule. Now, as long as you have this, it means that ay double prime plus by prime plus cy is equal to 0 is now being reduced to, because y is e power rt, so let me say y is e power rt, then you're going to see that ar square e power rt plus br e power rt plus c e power rt is going to be equal to 0, which is the same thing as ar square plus br plus c multiplied by e power rt is equal to 0. As long as you have this, you can see that this e power rt is never going to be 0 because it's an exponential function. So the only thing happens is ar squared plus br plus c is equal to 0. So that kind of tells you that in order to solve the differential equation, this one is like a differential equation, you just have to solve such an algebraic equation. So the relation between, I'll give you a chance to look at it carefully. Okay, so the relation is that the differential equation is turned into an algebraic equation, right? So that means that you can write this picture as follows. So AY double prime plus BY prime plus CY is equal to 0. I want to solve it. Then it is going to connect with each other by setting Y is e power RT. Then you want to do AR squared plus BR plus C is equal to 0. Right? So the equation in the lower part of this picture is easy to solve. Right? So the equation in the lower part of this picture is easy to solve. It's kind of pretty clear how to solve this equation. Right? So it's kind of pretty clear how to solve this equation. This is just the same. That R is equal to R12 is equal to minus B plus minus the square root of B squared minus 4AC divided by 2 times A. Right, so that's a quadratic formula. Everybody learned it in high school, so you can solve it. Now, how do you correspond to the solution here? Well, because of this correspondency, it can be written here that Y is still e power RT. So you're going to get 2 solutions. Y1t is e power R1 of t, and Y2t is e power R2 of t. Right, so this is the way how the solutions are 2 of t. Okay, so just a moment. Right, so this is the way how you really going to guess. Right, so this is the way how you're really going to guess a solution of a second order equation. A second order equation is going to be transformed to an algebraic equation by setting that Y is equal to e power of RT. No, that's the key idea. Okay, so Y is equal to e power RT. As long as you have that R entered into the picture, the correspondence is like Y is being transformed to R. In order to solve for Y, you just have to solve for R. As long as you have an R, you have an exponential function that serves as a good candidate of your solution. So for that R, it must satisfy a quadratic equation. It has 2 roots. And once you find the 2 roots, you raise both the roots into an exponential power, you get 2 solutions of your problem, right? So you get 2 solutions of your problem. So this is the way how you're going to solve. Okay, so how you're going to solve a second order equation. Okay, so how you're going to solve a second order equation, right? So that's the idea is first you try the exponential function, you take a lot of derivatives to that exponential function, you put them together, you set the quadratic form to be 0, and you get a solution. Okay. Now, this is just a very basic idea. Okay, so this is just a very basic idea, but you soon see some problems here, right? So why is the problem? Because some people is going to say, well, maybe the R1, R2 does not exist, right? So you don't know whether or not it exists, because in order to have this exist, you must guarantee that the quadratic discriminant is something positive. If the quadratic discriminant is not positive, then you cannot really you cannot really do this, right? So the quadratic discriminant has to be positive, right? So if it is negative, then you might have complex roots, and e to the power of a complex number sounds weird, right? So it's not quite a solution. And in the worst, in another case, is not that bad, but still not good. Is that if b squared minus 4 is equal to 0, then you're going to have 2 same rules. One solution becomes 2 solution collapses to 1 solution. Now comes the problem, right? So the problem here is about this whole methodology of guessing, right? So you can see that we are not really solving this equation. We're ready to guess this solution. And I can tell you that this is actually the main principle of this class. Okay, so during this class, we are really not telling you how to solve differential equations, because we really don't know how to solve differential equations. There's no real theory about solving it. I mean, there's very little theory. For example, like integrating factors, separation of variables. That's what we talked about before. But here, there is actually no real method, but rather to guess a solution. So this is really desperate. Okay, so to guess a solution. But this guessing methodology is problematic. Why it is problematic? Because imagine you're guessing something, right? So how do you know what you guessed is the solution? Maybe there are 2 solutions, right? There, like what happens here. There are 2 solutions. You guessed it, one solution, you guessed it correctly, but the other solution, you're going to miss it, right? So the guessing, in order to make the guess, okay, so in order to make the guess into a theory, you must guarantee that the solution is unique. So this is the philosophical terminology. So that means no matter what you're guessing anything, you have to make sure that the candidate, your guess is unique. For example, in a multiple choice question, I don't know how to solve this multiple choice question, A, B, C, D, which one I choose? Well, I guess it's A, but maybe it's A and a B, then I'm going to miss it because there are two solutions. So you have to guarantee that multiple choice questions is a unique solution, then I can guess it. As long as I get the right answer, the guess is complete, it becomes rigorous, it's a unique solution. So uniqueness is very important. So you can see that without having a real one solution, it kind of doesn't make really sense to say that there are two solutions. So how to solve this problem? Well, if you look at these two solutions, for example, AY1 double prime plus BY1, okay, prime plus CY1 is 0, it must satisfy this equation. Then AY2 double prime plus BY2 prime plus CY2 is also equal to 0. Then you can see that the solution y of t is equal to C1 y1 of t plus C2 y2 of t is also going to be a solution. So this is very easy to see because y1 derivatives, so basically this is going to tell you that a y1 double prime. So for example, I can multiply the first equation by C1, and I can multiply the second equation by C2. Remember, the right-hand side are both zeros, so no matter what you multiply, it's not going to change the right-hand side. So that's a C1 y1 plus C2 y2. You take a double prime plus B of C1 y1 plus C2 y2. You take 1 prime plus C of C1 y1 plus C2 y2. They're all equal to 0. So you won't have much problem with this, right? So that means if you have two solutions of this second order equation, you do a linear combination of these two solutions, you're going to end up with a solution again. So that's a very nice principle. It tells you that this equation not only has two solutions, but has infinitely many solutions, right? So that's it looks like the solution is not unique at all. It's not unique at all. So that means that it looks like this unique guessing theory is collapsing because I created even worse scenario that not only just one solution, but I have created infinitely many solutions. Is that good for everybody? Okay. So now how to solve this dilemma, right? So how to solve this dilemma? Well, this is not a problem at all because remember, when we solve a differential equation, there are two types of solutions. One is what we call a general solution. By general solution, it means there is a solution that must involve some constants, right? So by general solution, it means there's a solution that must involve some constants. And you have to determine those constants by what we call it initial conditions, right? So as long as you have the initial conditions, you can use those initial conditions to solve your problem, right? So you can use those initial conditions to determine a unique solution of your problem. Okay, so that's kind of what you would like to do, right? So you can use that unique solution to determine your problem. Okay, so determine your problem. So that's kind of the thing. Okay, so here it means that in order to have this solution, well, AY double prime plus BY prime plus CY is equal to 0 is going to have a very general solution. Y of t is like C1 e to the power R1 of t plus C2 e to the power of R2 of t. Suppose the B square minus 4AC, let's say discriminant is positive case, discriminant is positive, then you must have two different solutions where the R1 and R2 are two real numbers and R1 is not equal to R2. Then you're going to have this. Now, however, the general solution, this is what we call the general solution. Okay, so this is what we call the general solution, must consist of two constants, right? So general solution consists of two constants that you have to determine these two constants in order to determine a solution, right? So you have to determine these two constants in order to determine a solution. How do you determine these two constants? Well, you have to determine these two constants. That means you have to pass from the general solution to a specific solution, right? So you have to pass from the general solution to the specific solution by setting certain initial conditions. So what kind of initial conditions do we have here? Well, here in order, so question? Is there any question? If you have questions, don't hesitate to unmute yourself and just to let me know that you have questions. Okay. So that would be great. Okay, so highly welcomed. Okay, your questions are highly welcome. Okay, so now let's continue with this. Okay, so how do you find a specific solution? Well, in order to have specific solution, as before, we usually have like y of 0 is equal to some y0. So that's kind of one of the initial condition. But you have two constants to determine. You have two constants to determine. So that's not enough, right? So how do you do that? Well, in this here, you must see that if you have a second order equation, in order to have a specific solution, initial conditions have to reach up to the first order. Okay, so that initial conditions has to be the initial condition, initial value, and the initial derivative. So derivative is very important. Is that good for everybody? Okay, as long as you have that, you can use that condition to determine. So basically, it tells you that C1 plus C2, if you set t equal to 0, both exponentials are 1s. C1 plus C2 is y0. And C1 R1 plus C2 R2, because you're going to take a derivative, you set t equal to 0, this is going to be y0 prime. And from here, you should be able to solve for C1 and C2 explicitly. And once you solve for C1 and C2, you get a particular solution by setting the C1 and C2 to be the value that you found. Okay, so that's kind of the way how you pass from the general solution to a particular solution. Okay, so that's the kind of the way how you pass from a general solution to a particular solution. Okay, so that's kind of the nice idea. Okay, so that's kind of the nice idea that we use to work things out. Okay, so work things out. So now let's look at some examples. Okay, so here there is a nice example that comes from the spring semester 2010 exam 2 number 1. Okay, so here is a nice problem come from spring semester 2010 exam 2 problem number 1. Okay, so now this problem says, okay, so can you solve the initial value problem y double prime minus 4y prime plus 3y is equal to 0, where y of 0 is minus 2 and y prime of 0 is equal to 5. Okay, y prime of 0 is equal to 5. Okay, so now you want to solve this equation. It's like you go, okay, so this is how your standard procedure. Okay, so I would say standard procedure. Okay, so this is a standard procedure that's going to happen. Okay, on your exams. Okay, so you must practice through such a standard procedure in order to obtain your satisfactory credits for the problem. Okay, so that's this question says. Okay, so what's this question? Well, question says y double prime minus 4y prime minus 3y or plus 3y. So I would like to show you what's the standard procedure. Okay, so 4y prime plus 3y is equal to 0, where y of 0 is, so what are the initial conditions? Minus 2 and 5. So that's equal to minus 2, and y prime of 0 is equal to 5. So that's kind of the equation. How do we practice this equation in standard procedure? That's what you see on the exam. First of all, you should say, I'm going to say that I have an equation. So that's what we call it the characteristic equation. Okay, so it's good to write the word characteristic terminology, characteristic equation. What is a characteristic equation? Well, the characteristic equation is just this one. Okay, so basically this is what we call it the characteristic equation. This is just a terminology. Okay, not much. Okay, so here let me say, okay, so it's not much. This one is called a characteristic equation. By characteristic equation, it means this equation that's a polynomial equation, right? So basically, you just inherit the characteristics of your differential equation. That means the coefficients in front of the derivatives of the differential equation, but you are not going to do the differential equation. You're going to replace the derivatives by polynomial powers. So that's an algebraic equation. The whole thing is called characteristic equation. So it's just a name. Okay, so it's just a name. That we can want to unify, make a uniform name for what the object that we are studying. Okay, so that's what we call characteristic equation. As long as you have this, the characteristics. So this is the standard procedure on the exam. That I would strongly suggest you to write the word characteristic equation, the terminology out just in order to make the grader understand that you know what's going on. So characteristic equation means r squared minus 4 times r plus 3 is equal to 0. Okay, very important thing I would like to re-emphasize is that here there's a y, right? So there is a y, right? So there is a y here by the end, but there is actually this y is replaced by what? It's not an r but a 1. So that's kind of, there's nothing here. Is a good example. Okay, so remember the second derivative is the second power. First derivative is first power. Zero derivative is zeroth power. So that's just a constant. So that don't make yourself get confused with this. Okay, that's very important. There's just a constant 3. So then solve it. You solve the characteristic equation. Basically, this is like r minus 4, right? R plus 1. Sorry. So it's r minus. So it's kind of sorry. Right. So so I would have r minus 1, r minus 3 is equal to 0. So that's the solution to this problem. So that means that r1 is equal to 1, r2 is equal to 3. Right? So you have a real distinct root case. It's like what we discussed here. If the discriminant is positive, then you're going to have 2 real distinct roots for the characteristic equation. Right? So this is 2 real distinct roots. As long as you have real distinct roots, you must write another terminology, general solution. Okay, so you must write another terminology, which you're going to call the general solution. I would say general solution y of t is equal to c1 e to the power of t. You just raise the 1 to an exponential power, plus c2 to the power e to the power 3t. You raise the 3 to an exponential power. So that's a general solution. As long as you have the general solution, you have to find a specific solution. So you find a specific solution by setting zeros. So you say y0 is c1 plus c2. The t is equal to 0. So c1 plus c2 is minus 2. And y prime of 0 is, you take a prime, so that's a c1 plus 3 times c2 is going to be equal to 5. So from here, you can see that I want to solve for c1 and c2. So I will do this equation, subtracting this equation. So c2 is going to be equal to 7 over 2, where c1 is going to be equal to, so I want to have minus 2. So that's a minus 11 over 2, right? So that's kind of the values of c1 and c2, right? So that's kind of values of c1 and c2. Then you want to write last terminology. You want to say specific solution. Okay, so specific solution, right? So you want to write the last terminology, specific solution, y of t is going to put those coefficients there, minus 11 over 2 e power of t plus 7 over 2 e power 3t. Okay, so that's kind of the specific solution to the problem. So this is like the whole procedure. Okay, so this is like the whole procedure of how you write a solution on an exam. Right, so the whole procedure, that's how you write a solution on an exam. This is very standard. Okay, so it is a good idea that we have recorded the lecture that you can try to view it many times until you get really familiar with what's going on in here. Okay, what's going on in here. So that's the standard procedure you're going to use to solve this differential equation. Okay, so let's practice several more exercises. Okay, so here there's a much simpler problem. It says, can you find a general solution of y double prime plus 4y prime plus y is equal to 0? Okay, so that's kind of a simple example that says that y double prime plus 4y prime, okay, so plus y is equal to 0. How are you going to solve it? Well, this is very simple. You just said r squared plus 4 times r plus y is equal to 0. You get a solution. So r1 and 2 is equal to minus 4 plus minus square root of 16 minus 4ac divided by 2a. So that's kind of minus 4 plus minus is 12. So that's kind of 2 square root of 3 divided by 2. So that's minus 2 plus minus square root of 3. That's the solution. As long as you have the solution, you can see that the general solution, right? So you have 2 distinct real roots. So the general solution y of t should be equal to c1 e to the power minus 2 plus square root of 3, right? So that's the first solution of t plus the second solution of minus 2 minus square root of 3 multiplied by t. That's a kind of two solutions of this two general solutions of your problem, right? So two general solutions of your problem. Okay. So there are several remarks that we have been already mentioning, right? So there are several remarks that we have already been mentioning. The first remark says that you have to guarantee the uniqueness of the solution, right? So this is kind of a really nice remark, that you must make sure that your solution is unique, right? So that's kind of important. If you don't make the solution unique, then you cannot really say that the guessing. So our theory is about guessing, and you're guessing solutions, right? So you're guessing solutions. So as long as you're guessing solutions, you must make sure. Okay, so you must make sure that there is only one candidate that you would like to guess. Because if you don't know that there is only one candidate that you would like to guess, then you're making a lot of problems, because maybe you guess the solution and the solution, actual solution, is the other one, right? So you don't really know which one to choose. So that's the problem, that your guessing must be, your guessing theory must be grounded, okay, must be grounded on the fact that there is a uniqueness of the solution. Okay, so it must be grounded on the fact that there's a uniqueness of the solution. Okay, so that's very important. And the second thing is kind of going to be important is that what happens if it is not what we discussed, right? So what we discussed are the cases when the b squared minus 4ac, the discriminant is positive, right? But what happens if the discriminant is not positive? If the discriminant is not positive, then you're not going to really, okay, so you're not going to really have two distinct real roots of your equation, right? So you're not going to really have two distinct real roots of your equation, but rather you might have like a repeated roots or maybe complex roots. And how do you deal with those cases? So that's kind of thing, that if the b squared minus 4ac is equal to 0, then you have two repeated real roots. And if the b squared minus 4ac is less than 0, you have two complex roots. And in both cases, you really don't know how to solve these differential equations. Right, so that's kind of the thing we want to resolve in our as a continuation of today's lecture. So let's say how do we solve real repeated root case? Okay, let's first review what we have been doing so far, right? So what we have been doing so far is that you want to solve a linear, homogeneous, constant coefficient second order ordinary differential equations, right? So that's ay double prime plus by prime plus cy is equal to 0. Now what you're going to do is that you're going to inherit the coefficients be in front of y derivatives and y's and y derivatives, ABCs, you inherit them into a polynomial power. So that's AR squared plus BR plus C is equal to 0. As long as you have that, you solve for the solution by a quadratic formula, right? So you solve for a solution by a quadratic formula. Okay, so you solve for a solution by quadratic formula. As long as you have the solution by quadratic formula, you can see that the solutions are y1 is equal to e power r1, e power r2. Okay, so but that's only works if the discriminant is positive. It only works if the discriminant is positive. But if the discriminant is negative or maybe equal to 0, then it doesn't really work. You won't really have two distinct real solutions, but rather you might have like repeated solutions, or you might have complex solutions. So that's kind of the issue. Okay, so here we're going to deal with the case. Okay, so here we're going to deal with the case that you have ay double prime plus by prime plus cy is equal to 0, and your characteristic equation ar squared plus br, remember, this is what we call it the characteristic equation. Okay, so, and actually it was written here, right? So this is what we call it the characteristic equation. Okay, so as long as you have this characteristic equation, okay, so as long as you have this characteristic equation, you would like to solve this characteristic equation by quadratic formula. So that's r12 is equal to minus b plus minus the square root of b squared minus 4ac divided by 2a. That's the characteristic equation, right? So, and as long as you have this characteristic equation, we're going to discuss the case when b squared minus 4ac is equal to 0. Okay, b squared minus 4ac is equal to 0. That means this you're going to have r1 is equal to R2, let me call it R, is equal to minus B over 2. There's only one root. But imagine, okay, imagine the problem. Let's say imagine the problem has two initial conditions. So like y0 may be equal to y0, and y prime 0, you also know it is equal to y0 prime. If you have two initial conditions, then if you just have one solution, it means that I will have y of t, right? So it's like the first solution is C1, right? So e power of RT. And second solution is also C2 e power RT. So that's kind of, it looks like the solution is C1 plus C2 e power RT. And there's only one effective constant C here, but you have two initial conditions. So it looks like there's a contradictory, right? So that's our previous method really is not working. Okay, so it's not working at all because you reach such a contradictory that you might have two initial conditions just to match like one unknown solution. So you have a redundancy of your equation. So this is not really the idea, right? So this is not really what you want to work out, right? So this is not really the idea. It's not the good idea to do this. So what's the idea? Well, the idea is that there is going to be a way to resolve this problem by saying that the general solution for a real repeated root case, okay? If you have a real repeated root case, then the general solution is not going to be just the e power RT, but you're going to insert a t, okay? So insert a t to make e power RT into t times e power RT. You're going to say, this is the second solution that you would like to find. Okay, so this is the second solution that you would like to find. Okay, so this is actually, this is what we call it, sometimes called the golden principle. Okay, so let's say, so maybe I'll use another color. Okay, so it's because it's, so let me use, okay, so maybe use this color. Okay, so it is called so this is kind of two. That's not a good idea. Okay, so just a moment. Okay, so let me find good color for this. Okay, so so maybe I will use this color. Okay, so it is called. Okay, so it's called the golden principle. Okay, so by the golden principle, it means that we are going to have we're going to have the fact that this first solution y1t is e power RT, and then they're going to say that y2t, okay, so is kind of going to be t times e power RT. So there's t times e power RT inserting here. So that's kind of the principle is why it is golden, because that you want to create another solution of your problem, you just insert the t's. Okay, so the problem here is a scarcity problem. By scarcity problem, it means that we're lacking solutions. We're just lacking solutions simply because the roots are going to be repeated. I will have only one root r in my pocket. I just have one root r in my pocket. So that's kind of the problem because I'm in scarcity, right? So I'm lacking solutions. I don't have another r, right? So I just have one r in my pocket. And if I just have one r in my pocket, then I will going to have problems with finding a solution, because another solution, because I'm lacking roots. I'm lacking roots. So the golden principle is simply telling you that whenever you're lacking the root, you should multiply by t to the equations, to the solutions that you already have. Let's say you already have solutions, then you should kind of insert t's. You continue to insert t's until you reach the satisfactory number of solutions. Here, you just need two solutions, so you must insert one t. So that's kind of the problem with the golden principle. You insert a t. Okay, as long as you insert a t, then you can say that the general solution takes the form C1 e power RT plus C2 t times e power RT. That's just your general solution. As long as you have the general solution, you should put initial conditions there, you find solution. So that's what we call it a golden principle. Okay, so as long as, so the reason why we say golden is because as long as you are lacking solutions, right? So you're lacking roots, that means you're lacking solution because you want to build from each root a solution and then combine them by linear combinations. Now for each root, you're going to have a solution, and as long as you are lacking, okay, so as long as you are lacking the roots, you're in a scarcity, you have no money in your pocket. How do you make yourself rich? Well, you're going to use the golden principle, namely multiply by t's. Okay, so multiply by t, you created a solution that did not exist before, right? So as long as you created that solution, you combine them, you get another solution. So that's kind of the idea that we call it the golden principle. Okay, so to build general solutions. Okay, so here we would like to show you some nice examples. Okay, so here we would like to show you some nice examples. Okay, so for example, here this question says, can you find the general solution of this equation? Y double prime plus 4 times y prime plus 4 times y is equal to 0. Okay, so in order to solve this equation, you're working with this y double prime plus 4 times y prime plus 4 times y is equal to 0. Remember, the question is only asking you to get a general solution. Okay, so it's only asking you to get a general solution. So in order to get a general solution, you have to say that the characteristic. So it's the same thing that you're going to say, right? So you're going to say that the characteristic equation is going to take the form r squared plus 4 times r plus 4 is equal to 0. And therefore, you see that r plus 2 squared is equal to 0. So ry is equal to r2 is equal to minus 2. That's the solution. As long as you have that solution, you're going to say that you use the golden principle so that the solution y1 is equal to e power minus 2 of t. And what about y2? Well, y2 is a golden principle, t e power minus 2 of t. So the general solution, right? So the general solution is going to take the form, right? So general solution is going to take the form y of t is a kind of c1 e power minus 2 of t plus c2 of t e power minus 2 of t. That's it. So that's kind of how you make use of these kind of golden principles in order to create general solutions. Okay, so that's kind of that. And here's one more thing I'd like to mention is that I have been emphasizing many times that you must look, okay, so you must look at the requirement of the problem. Okay, so you must look at the requirement of the problem as much careful as you can, right? So here it says that it's just looking for a general solution. Okay, so that you don't have to put initial conditions. But what if they put initial conditions? For example, this one. Can you find a solution of this initial value problem where there is initial conditions, right? So that's what's this equation talking about? Well, this equation is y double prime minus y prime plus 1/4 of y. So that's y double prime minus y prime, right? So plus 1/4 of y is equal to 0 with initial conditions. Initial condition y0, 2, y prime 0, 1/3. Okay, so that's y0 is equal to 2, y prime 0 is equal to 1/3. Right, so you have this. How do you solve this equation? Well, again, you have to work with the characteristic equation, right? So, characteristic equation, right? So you have to work with the characteristic equation. Okay, so the characteristic equation is going to say that the characteristic equation is r squared minus r plus 1/4 is equal to 0. So this one has been can be rewritten as r minus 1/2 squared is 0. So that means the solution r1 is equal to r2 is equal to r is equal to 1/2 characteristic roots, right? So sometimes these roots of the characteristic equation are called characteristic roots, but this is only okay. So this is only a terminology issue. Okay, so this sometimes called characteristic roots. As long as you have the characteristic roots, you can see that the general solution. So the general solution. Right, so as I said, the general solution should be a linear combination. So that's a c1 e power of r is 1/2 of t plus c2. Are you going to use e power 1/2 of t? That's not enough. You have to apply a golden principle because the two roots are the same. So that's a general solution to the problem. Okay? So that's a general solution to the problem. As long as you have that general solution, you should find particular solutions by putting initial conditions into it. So the C1, okay, so plus t equal to 0, this is 0, so there's nothing. So that's a 0 is equal to 2. So that's already give you C1. What about C1 y prime? Well, y prime means that's 1/2 of C1 e power 1/2 of t plus the derivative here is a C2 e power 1/2 of t plus C2 t 1/2 e power 1/2 of t. You're going to set t equal to 0. This is going to be equal to 1/3. So that's the derivative relation. Now, if t is equal to 0, you get 1/2 of C1 plus C2, and t equal to 0 don't have this one. This is going to be 1/3. And C1 is already solved from here. It's 1, so that's 1/2. So C2 is like 1/3 minus 1/2 is minus 6, 1/6. That's it, right? So C1 and C2 are both solved. So that's particular solution. Okay, so that means the particular solution. Okay, so particular solution is going to be equal to y of t is equal to, okay, so it's equal to e power 1/2 of t minus 1/6 t times e power 1/2 of t. So that's kind of the way how you're going to find the particular solutions. Okay, so, and sorry, so maybe there's an error in the numerics. Okay, so let me just make sure. Okay, so here's the problem with C1. C1 is 2, right? So if C1 is equal to 2, then this is 1. Okay, so this is minus 1. So that's actually minus 2/3, right? It's minus 2/3. So that's actually 2 on minus 2/3. So just a numerical issue. So that also reminds us that one should not make mistakes on your exams, right? So that's also reminds us that it's important to make sure that everything is calculation is correct on your exams, right? So that's minus 1, so that's minus 2/3, so minus 2/3, so that's it, right? So that's kind of the way how you find a particular solution. Okay, so that's kind of the way how you find a particular solution. Okay, so now let me summarize. Okay, so let me summarize today's lecture, right? So we've been talking about the solving linear homogeneous equation. Okay, so constant coefficient ay by prime plus cy is equal to 0. Now, what's the standard procedure? Okay, the standard procedure is to start from the characteristic equation, right? So you write the characteristic equation. That will going to be AR squared plus BR plus C is equal to 0. Then you're going to find the characteristic roots. Okay, so then you're going to find the characteristic roots. That's R1 and 2 is minus B plus minus the square root of B squared minus 4AC divided by 2 times A. At this lecture, we've been talking about the case when B squared minus 4AC is positive, as well as B squared minus 4AC is just equal to 0. And we talked about these two cases. And in both cases, you're going to create y1 of t is e power of r1t, that's y2 of t is equal to e power r2t. These two solutions are sometimes called fundamental solutions. But this is only a terminology. Okay, so these are terminology issue. Why they are fundamental solution? Because they look like building blocks of your general solution. Okay, it doesn't quite, I will come back to the fundamental solution terminology in the next few lectures. So it's just to mention here, it's called fundamental solutions. And how do you create a fundamental solution for the common root case? So that's R of t, and y2 of t is not going to be e power, so R is going to be t times e power r2 of t. That's what we call the golden principle. So in general case, you must reach these fundamental solutions by certain strategies of constructing them. It can be like raise everyone to exponential. It can be like raise the common one to exponential and raise a t to the other one. And as long as you have the fundamental solution, you reach the level of general solutions, right? So you reach the level of general solutions. It's going to say that y of t is like a linear combination c1 y1 of t plus c2 y2 of t. As long as you have the general solution, you must reach from the general solution, all right? So you must pass from the general solution to a particular solution by setting, okay, so by considering y0 is y0 and y0 prime, right? So initial conditions, initial value and initial velocity, that's going to give you a particular solution in y of t. So that's a particular solution. Okay, so that's what I want to say for today's lecture. Okay, so we're going to come back to the next lecture and then we will continue with this discussion. Okay, so that's what I want to say for today's lecture, and I'll meet you in the next lecture. See you in the next lecture.